Our first presenter, Ulrich Drepper. Ulrich joined Red Hat again in 2017 after a 7-year hiatus. He is enduring his previous stint, also was a member of the Office of CTO. In that capacity, he is looking at upcoming technologies for products and internal applications. His focus is mostly on machine learning and low-level, high-performance computing, as well as alternative computer architectures. Previously, he was working at Goldman Sachs in the technology division. At last position was as member of Data Science Research Group, focusing on the development of models and various types of stochastic algorithms to add in the operation of the technology division. His main interests are in the areas of low-level technologies, like machine and processor learning, architectures, programming language, compilers, high performance, and low latency computing. In addition, he is interested in using statistics and machine learning for performance analysis or programs and security of applications and OS environments. He worked on several revisions of the POSIX standard and was invited expert of both the C and C++ standard committees. So please, welcome Ulrich Drepper.
All right, thank you. So it's not the talk you originally saw on the schedule, so this is just something which I have in my bag of talks which I can give. And I was simply asked to give something, and I think this is one of the more relevant talks these days. But before I start there, so who actually knows what FPGAs are? Okay. Who actually programmed them? Even fewer, of course. All right, so those folks might actually be bored because I'm actually trying to get to the very bottom of this. So I'm starting very low with no expectations that they actually know something about this, the topic itself. But as I said, this is something which comes up now more than at any point in time that I can remember. So for those who are reading Hacker News or something like that, so every day there's some article about FPGAs out there. And you might have wondered why this is so interesting right now. So we're going to look at this. So don't be confused by saying here January 2018. As I said, this is a talk which I had given before. So this is just something which I can't repeat easily. And normally during my talks, so I don't mind to be interrupted. So if you wait until the very end with your questions, you might actually forget about them. So feel free to try to interrupt me. It's very hard. So the lights are very bright here, so I don't really see that much. So you have to actually make yourself known. Okay, so before we actually start looking at the specifics of FPGAs, so let me introduce what is the concept of compute in the first place. So what we mean by that is just that we have a set of input data, and we are expecting output in a certain form, and the stuff in the middle there, this is some implementation of a kind of a function in a mathematical sense, so which provides using the input a specific output. In some instantiations of this, there might also be state involved in there. Somehow this is the fixed function includes some information about the previous inputs, etc., and the previous outputs as well. But in general, this is the concept we are looking at, and this serves us well on both the hardware side and the software side. So there's not really any difference there. So you can have a normal hardware circuit like you see it here on the left-hand side, which is exactly the same. We have a couple of input lines of some sort. Maybe we don't really have that many, but it doesn't matter. And we're expecting some form of output. And the same is true, of course, for programs where we have either in the form of files or sensors or whatever inputs coming in, and we are expected to produce a certain output. And FPGAs are not any different there. They're falling somewhere in the middle between them. So they are hardware, but they're also software to some extent. What this means, well, we're going to look into that. So, but before we can do this, let's revisit something which more people are probably familiar with, which is the software side. So, and when I say familiar with, this is a cursory knowledge from what I'm usually used to. So when I talk to people, so how does a processor actually work? So very, very quickly, they get to, oh yes, something here, something there. So, but I don't actually know how it actually means. So we want to change this here. So we are going to look at a processor, how it actually works, because this will help us understand how we can actually utilize something like an FPGA. So this is the schematic of the first real PC processor in this sense, so the 8080, 8085 from Intel. So the schematic was published by Intel very early on, except for these two white boxes up there, the WZ. They kept them secret, so they never told anyone about those things in this sense. But this was reverse engineered and verified that this is basically how the processor looked like. So that's very simple compared to what processors are looking like today, and this is why we're actually looking at this. So because we can actually understand everything about this processor, we can actually simulate everything. So, and if you're interested in this, I actually have simulators written myself, which are simulating every single tiny little sub-cycle detail of this processor and run code on it. So it's really fascinating. So we have at this point now here. I have on the left-hand side here, I have spelled out 3 different types of instructions which we can execute. So, and the way the processor actually works, it divides every single instruction execution in a number of different steps. And in fact, in the way this is actually implemented on the 8080, it has even 2 levels of steps. So we have the memory steps, which are called here M1 to M4, and not all of the instructions are needing all of these memory cycles. And inside the memory cycles, you have individual time steps. And you see them here listed as T1 to T4 occasionally, but not always there is a T4. So this is the minimum level at which all of these operations work. And, well, let's just go through this. So assume now we have an instruction, which is this LDA instruction, which means load into the accumulator. The accumulator is a special register and inside the CPU itself. So at the first time step, what it does is, you can see this up there, PC out. So what this means is that it has to actually fetch the instruction. And what is involved in there is highlighted on the left-hand side. So there's the instruction decoding hardware is there. The timing control is always involved in that. The PC is the register which currently holds the address of the next instruction. And that instruction is put into the address buffer and then emitted to the outside in the address pins A0 to A15. That's addressing, it's providing the address to the RAM chips which are attached to the CPU itself. So that happens in the first cycle. So then we are going to M1 T1, the second time step of that. So you see here, what it does is, well, I have looked at the current instruction, so we have to go now to the next instruction. So this all happens while in the background, the RAM chips are working, because they're not working instantaneously. So they have to switch to the new address, etc., and these kind of things. And the CPU, therefore, can use the time to do something else. So there's parallelism going on at this granularity. So in this case, the PC has to be incremented, and the register block, which you see there, has a special piece of hardware attached to it, which is called the incrementer. And therefore, this incrementer itself gets as input the PC value, increments it, as the name suggests, and then stores back into the PC register the new address. So means we have implemented PC equals PC plus 1. So the next time step, we are ready to receive the byte which is encoding the instruction. As I said, the RAM chips don't work instantaneously. So we have, the RAM chips got time to react during the previous cycle, the T2 cycle. And in T3 cycle now, we can read the byte from memory on the data bus, which you see at the very top there, D0 to D7, which are the pins connected to the data bus coming from the RAM chips. They can now receive the data from memory itself, which is the byte for the instruction. That stuff has to be stored then somehow internally. There's the register TMP IR, is the instruction register. It gets stored there, and right then when it becomes available, the decoder logic springs into action and decodes the instruction. So how that works, we'll see some example of that later on. But basically, this is a big lookup table, which says if the byte looks something like that, then the following are the signals according to these tables here on the left-hand side, that which we have to look at. So, and this works that late. We don't have to, because take a look here. All the three instructions which you see here are sharing the same 3 timestamps in the first cycles, in one cycle. So this information doesn't have to be encoded into the instruction itself. It's always the same. But from then on, the different timestamps might do different work, and that's then encoded into this lookup table, which is encoded into this block over there. So this is stored in what's called the PLA inside the chip itself. But you really can think about this as a big hash table if you're used to software. So next time step, there is nothing to be done here. So this is then usually even skipped in many situations. But then we get to the next one, which is PC out. So for the LD, we have to do it again because it expects a parameter to the LDA instruction, which is in this case the address. The address is 16 bits. Sorry. Which means that we have to actually have to transfer more than one byte to the address buffer to actually select read more than one byte from memory to get the complete address, and that's what you see in the next couple of steps. So the PC out, again, the address of the next byte in the instruction stream is pulled out. We increment it. And then we are storing the first byte in the Z register, which is one of these hidden registers which the CPU has. Then we repeat the same thing again, and the resulting second byte, which we read in from memory, is stored in the W register. So these are 2 8-bit registers. Together, they are serving as a 16-bit register. And you can see now this combination of the WZ register are now containing the 16-bit encoded address after the LDA byte, which is encoding the instruction itself. So we have read 3 bytes, and we can now actually execute this instruction, which happens in the next step, where we are emitting the WZ register, 16 bits, onto the address buffer, so that once the appropriate time is over, we can read on the data bus the appropriate byte. That's it. That's how a memory load happens. In this case, the byte is not stored into the temp register because it's not an instruction. It's actually directly stored in the accumulator, which you see there highlighted in the diagram. So why do I delve into these kind of details? Why do I mention this? Well, this is a simple example of a kind of a machine and encoded. So it's a state machine, as you will probably call it, which does something according to a program logic. So you could write software which looks exactly something like that, but this is how processes actually work. So if we can write something in software or in hardware which looks something like that, we can actually write our own processors. So I don't want to say that 8080 is any kind of state-of-the-art, so of course not. So we have since then made quite a lot of progress. In processors, we have gotten wider data buses, so we now have 64 bits. We have wider internal buses, so most of the x86 world, for instance, internally, at least Intel has already 256 bits, AMD in the next revision as well. So the data paths which you see here on the right-hand side, they're all 8 bits, except for the address lines out there. So we can do a lot better nowadays. We have more registers. So here you can see we have in total 7 general-purpose registers, which is not really that much, and one of them is actually not really that general-purpose, the accumulator. We have wider registers. We have more ALUs. So in this case, there's one single ALU, which is the arithmetic logic unit, which is the one which actually can perform any of the operations. So these kind of things are much better nowadays. And it looks in the extreme case, so this is a Skylake architecture from Intel, so in the block overview. So not to be compared. It's not at the same level of granularity which I've shown before, but that's as low level as you might want to get it today. So these processors are extremely, extremely complicated now. So each of these cores, I don't know how many hundreds of millions of transistors are necessary to implement one of those. And we have now even on a laptop, something like this, 4 of those in each of the processors. So it's tremendously complicated. But what is important is they are not working any differently behind the scenes than the 8080. So there is some microprogramming going on which is guiding the processor through a series of steps to execute the individual instructions. We just have more things happening at the same time and more things in parallel because we have wider operations. But nothing really changed. Where we have lots of problems coming to these years, so as compared to the days when we had the 8080, where we only had to wait for memory for one of the memory cycles. Nowadays, the discrepancy in speed between the main memory and the processor itself has grown tremendously. So we are talking about something like, well, on a normal CPU, something like between 150 and 250 CPU cycles to get data from the main memory. The reason for that is that we have basically a lookup like this. So we have a CPU, which is this gray block here, the horizontal one, connected using some form of pins. It's usually a BGA. Nowadays, a socket, so a ball grid array, connected to some socket on the motherboard, which has then lanes, has then basically connections going over all across the motherboard itself to another connector in which we can plug in the RAM chips. And, well, if any EEs here, so electrical engineers, they will know that, well, this can only happen so fast because, well, there's capacitance to come over to actually get the signal from one end to the other. And you can already imagine that how much capacitance is in there. So the ball grids themselves, all the connections, all the big metal connections on all the sides. So there's lots of capacitance for every single line, and therefore we cannot really spend that much of energy to overcome this kind of capacitance, that much of the impedance. So we have nowadays, I think, 1.2 volts only of available for the connections themselves. So this is really, really timing critical for that. So we therefore have to limit ourselves in the way we can use memory on these kind of on normal processors, and we have to spend a lot of time optimizing applications so that we're working around the limitations of memory. So another problem where with normal CPUs we have is if we want to communicate with the outside world. So if you have a normal desktop CPU and so on, it has connections to dedicated ports which are already on the motherboards, like a USB, and we have PCIe connections and so on. But if you want to hook up something like some other hardware sensor or something like that, these kind of things are not really that easily doable because all the connections which exist out there on the CPU itself are already taken up from. So if you have in embedded workloads specifically, you might actually want to connect all kinds of stuff in there. So something as simple as, let's say, on home automation systems. So you have to get all kinds of sensor inputs. You have to control some display. You have to have keypads inputs and so on. So these are things which you either can have in additional chips or sets of chips outside the processor to handle with them, or you need to have many input lines available, which is not really that easily doable from normal processors. So specialized embedded processors like this, so this is an NXP, so that's an ARM-based one, has lots and lots of input lines and so on, but that's not usually the case. So we have, and even those numbers which you see here, so they're not all the same. So they have differences. So not every single line can be used for everything. But even if you add them up, that's not such a high number, which you're usually happy with. So in many situations, you need a lot more connectivity than this can afford you. So we have, therefore, limitations in the current way we're building processors. But on the other hand, we understand how we build them. We can actually model CPUs quite easily. And, well, let's see where this takes us. But before we can go there, I have to go a little bit on the hardware side, because FPGAs don't really exist in software alone. There's a lot of hardware knowledge which you also have to have. So this is something which hopefully everyone who has a CS background has seen at some point. So EEs, of course, have lived this thing. So we have gates, which many of them are. Well, we can have quite a lot of different ones of them. The ones which most people know about are AND gate and OR gate. And here are the truth tables for them with two inputs. On the left-hand side is the AND one, on the right-hand side the OR one. And I think this is not any surprise to anyone. So for the inputs A and B, we're computing the output Z. So when I think back, that's normal compute. So we have a couple of inputs and we get an expected output. And the use of truth tables like that is very convenient. But I was always unhappy that people are concentrating on these two gates, because these are actually not really that interesting gates, because they're not what is called universal. On the other hand, there are universal gates, which are the NAND gate and the NOR gate, for instance. There are a couple more, because universal in this case means that we can replicate any other gate using the NAND gate and the NOR gate. So they are very similar to the AND gate and NOR gate, except that the result is negated. And so I'm not going to the details why this is the case, but but just in short, with just AND gates, you cannot implement an OR gate. And with just OR gates, you cannot just implement an AND gate and a couple of other things. But with a NAND gate or a NOR gate, you can implement an OR gate, a NAND gate, a NOR gate, etc., all of these kind of things. So this is why they're called universal. And what you see here is the implementation there. So on this side here, we're implementing using NAND gates at the top, just a normal AND gate. So that's very, very easily doable in this case. So, and the other ones as well. So not really that tricky. But the NAND gate and NOR gates are not the only universal one. There's one which is very convenient, which is called the multiplexer. The multiplexer in this case has 3 inputs, where we have inputs A, B, which are expected, can be changing, but not usually expected to change in this case. And there's a selector line. The selector line in this case is a single bit as well, because we have 2 inputs. So if we would have 4 inputs, then the selector line would consist of 2 input lines, so 2 bits, because what it does is, if it is 0 in this case, it will take A, and if it is 1, it will take B. And that's, you can also see in the table here. So, and it's easily extendable. So if you have 4 inputs, you have 2-bit input lines for S, and it creates numbers from 0 to 3, and it selects the appropriate input line. That is also a universal gate. And it's very easy to understand in the sense it's nothing but a big lookup table in short, if you want to use it this way. And that's the key, and the reason why we are going to that, for the FPGAs, because FPGAs are based on basically this type of gate. So let's go through that. And I have to add at this point that FPGAs are well understood. We know how they work, but for most cases, the manufacturers are pretty secretive about them, how they actually, well, not necessarily how they are working, but how they get programmed and so on. But there is one specific one, which I'm going to introduce in a bit, which has been reverse engineered, and I'm going to talk mostly about that one, but everything is generalizable to all the other ones as well. So assume we have a construct like this, and it might look more complicated than it is in this moment. So we have in this case 3 inputs, A, B, C in this case, which are all connected to multiplexers, and therefore with these 3 inputs we can select with the encoded number one of the, in this case, 8 inputs on the left-hand side to arrive at the output Z. Hopefully you see this. So this is just, in this case, using simple multiplexers with 2 inputs and so on. But every single one is selecting exactly one of the 2 inputs. And therefore, we can, using this combination, select one of the inputs on the left-hand side to appear on the right-hand side as the output. So it's very simple like that. So in theory, we could have implemented this differently as well. In this case, we could have, as I mentioned at the beginning, have one single multiplexer with 8 inputs, and where the S, the control bit, has 3 bits. But we can also split this out into a number of different 2-input multiplexers and so on. So that's an implementation detail. And the more advanced your manufacturing process is, the better probably you choose a method which is faster or uses fewer resources, etc. So, and what is also possible is to have, instead of 8 inputs, or selecting between 8 inputs, having more of them. This is another implementation detail. So this is specific to the one chip which we are going to look at here. So hopefully this is clear that this works. So depending on how we are selecting ABC, we can select one of the inputs. So the interesting the thing which makes an FPGA interesting is that these inputs which you see here, which are appearing at the outside, they are actually not dynamic signals in the sense that they will change over time. Those are one-time programmed when the chip comes up. So there are SRAM cells which keep their content throughout the lifetime of the FPGA, so until it gets rebooted or reprogrammed and so on. But the ABC signals at the bottom, those are the ones which are changing in the duration of the program running on the FPGA. So with that, we can build up, similar to what I described before, we can build up a lookup table. So we have a given bit pattern which is stored in these SRAM cells, and which then is appearing depending on the number encoded into the ABC. Signals appear on the output. So we can program anything. It's a universal gate. So how does it work? So if we want to implement an AND gate, for instance, with 3 inputs, we would just say, well, we're building up the lookup table, like we have it here on the left-hand side. And then the Z column is the ones which we're storing in the SRAM cells of the FPGA. And all of a sudden, then, if we are providing the inputs ABC according to whatever we want to get, we get the appropriate results stored in at the output. The same we can do for the OR gate, and the same we can do for a full adder. Nothing had to be changed on the hardware except the content of the SRAM cells. So, and that might now ring a bell. This is exactly the promise of an FPGA, where you have hardware which works at hardware speeds, but it's completely controllable in software. The software controllable part is the storing of the appropriate piece of information in the SRAM cells which are serving at the inputs here. And the only thing I have to do is, between running different programs on it, so in this case for an OR AND or a full adder gate, is to change out the content of the appropriate inputs there. And all of a sudden, the same thing works quite differently. So I mentioned that we have one FPGA which has been nicely reverse engineered. So the guy on the bottom right, Clifford Wolf, currently resides in Vienna, actually, not too far, has done a tremendous amount of work of re-engineering a very, very small FPGA, which is called the ICE40, and which is available in various different forms. For instance, this one. So if I would have known, I've given this talk here, so I would have brought my chip with me. So I have a couple of those, including this specific one, which you can just plug into your USB port, and you have an FPGA running. So, and more than that, we not only know how it works, Clifford has written an entire tool chain for that. That's the novel thing now. So before, most of the FPGAs have to be programmed using the proprietary tool chains from Xilinx, Altera, etc. So these are tremendously complex pieces of software. And, well, there are free versions available, but they expect that as soon as you do something serious, you have to pay them big money to actually use their professional ones. But with that, we have a complete tool chain available. And I have this then usually doing my presentations running on my laptop. So where in real time, write the program, compile the program from what is called a hardware description language, either Verilog or VHDL, into the bits, into the output, which can then be programmed onto this chip. And we have a completely, as I said, freely available tool chain. So on Fedora, you can just install the thing and it works out of the box. The basis of the ICE40 is a logic cell, as they are called, which looks like this. So this is similar to what you have seen before. So the LUT4 is this lookup table with 4 inputs. Exactly what we have looked at before. So now instead of 3, it's 4 inputs. And to program that, obviously, we need 16 SRAM cells. So we have 4 inputs, 2 raised to the power of 4 is 16. So we need 16 input cells. So this thing gets programmed using 16 bits. Then it's fully programmed. The other things inside the logic block which can be programmed is this little AND block at the bottom left here and the output block over there. So all the gray ones can be programmed. In addition, we have an AND gate, which is the white one here on the top left. I'm getting to that next time. So, but the other thing is over there in the middle, and that's a D flip-flop. Again, we are going to talk more about why we need that a little bit later. So, but that's the basic logic block inside the specific FPGAs. For other FPGAs, more complex ones, you will see larger ones. You will see a lookup table, a LUT with 6 inputs or something like that, and a couple of other different pieces of logic there. But at the bottom of it, all of them usually consist of one type or perhaps a few types of these kind of logic cells, which are then duplicated. So every single, on the ICE40 specifically, we have a logic block which consists of 8 logic cells. So, which makes for a total of 33 inputs, because not everything is what is an input here actually has to exist as an input for the logic block, because as you can see, they are actually chained. So this and the output of this AND here is used as an input for the next cell. And only at the end of the chain and at the beginning of the chain do we actually have outputs and inputs available. So it's really not that critical for you to see all the details here, though. But this is simply one single logic block inside an FPGA, which is programmed in a certain way. So let's see how we can actually use this kind of thing. So these are the basic implementations of what is called the adder. So it's a half adder, which is simply adding 2 numbers, and the full adder is one which adds 2 numbers plus the appropriate carry bit and also produce, etc. So these kind of things are fundamental to the way we do arithmetic with a CPU even nowadays. So even though we have to, for high performance ones, we have to look a little bit differently. But how do we chain them? So and this is very much how we have to do it with FPGAs as well. So if we want to add numbers which consist not of just single bits, but let's say multiple bits, we can just take the full adder as it is represented in this case here and chain them together, where the carry outputs of the lower bit full adder is used as the carry in of the next higher bit full adder. And at the output is we get a carry out, which is, in this case, if we're handling just 4 bits, we are having the overflow carry of the 4-bit addition in this case. So this is how arithmetic worked all the time, and this is also how this actually works in these logic blocks inside the FPGA. So there's some special logic built in to perform this kind of arithmetic. So these carry chains using the special AND block have been carefully designed so that they can be used to implement an adder, which is, it's a fundamental operation which we have to do all the time, and therefore it's worthwhile spending something. So in theory, we could have done without that. We could have implemented using the universal gate of the multiplexer. We could have implemented a full adder in a different way, but that would have been a lot more work. We needed a lot more logic cells to actually implement this, and in the end, it would also have been slower. So with this, we actually don't have to spend too much work. We just have to configure the appropriate AND input, which is driving or which is controlling whether we are actually propagating the signal statically when we are programming the logic block. And all of a sudden, we can transform this single logic block into an 8-bit adder. If we want more than that, we can even chain 2 or 4 of those logic blocks in sequence by having the output, so the carry output of the topmost one, in this case, feed into the input of another PLB. And we can easily implement a 1632-bit adder. But more importantly, at this point, I should also point out, we can also not just implement powers of 2, as we have it nowadays in CPUs, of course. I can create very, very easily, and with just the right amount of resources, an adder which implements, let's say, 23-bit arithmetic, because I just don't use the rest of the logic cells. That's an important thing when it comes to FPGA programming. So if you have followed the development on the sun and on the side of the GPUs and so on, they have competed, especially in the machine learning world, by having different types of arithmetic than we have seen before. So usually, for instance, we always had the usual integer arithmetic, 8-bit, 16-bit, 32, 64, and so on, and we had floating points and 32-bit and 64-bit. Nowadays, they are competing by saying, oh yeah, we can also do 16-bit floating point, 8-bit floating point, etc., and these kind of things, because this might fit a certain set of problem much more easily and can be implemented, therefore, with fewer resources and with higher throughput, because we can have 2 or 4 times as many operations going on at the same time. Well, but if someone needs, instead of only 13 bits of precision, for instance, 13 bits, well, you have to use 16 bits on the GPU. But with an FPGA, if you wanted to, if you have enough energy, you could write the entire pipeline of arithmetic with exactly 13 bits and use just the resources for that. So we have a lot more flexibility when it comes to that. But in general, so the ICE40 based FPGAs are, even though this should already be somewhat impressive to you if you have never seen this kind of thing, they are trivial by comparison to the really advanced ones. So the ICE40 is really meant for simple embedded use cases and so on, but the big ones have a lot more logic in there, and they can do a lot more operations. And instead of just having special logic for addition as we have it here, we have in big logic, big PLAs, FPGAs, we have additional blocks which can do multiplication. So there are so-called DSP, digital signal processing blocks inside an FPGA, which can do all kinds of higher level operations in there. So they can be customized a lot nowadays. So looking at this structure, the PLBs, the logic blocks, we are not even at the top level yet. So we have many of those, even in the simplest of the FPGAs. So this is the block diagram for the smallest possible ICE40 FPGA which we can get. It's the 1K one. And you can see there are quite a few of these PLB blocks which I have mentioned there. Each of them can implement, for instance, an 8-bit adder. So we can have multiple of those. In addition, every single FPGA has RAM on it of various sizes. This is usually then a static RAM, very, very fast one. But we can also have attached to the outside world dynamic RAM. But unlike normal processors, which have a memory controller built in, we would then actually have to write the DDR protocol ourselves inside the FPGA to actually talk to DRAM. So this kind of thing, the software for that or the programming for that, you can buy from the appropriate vendor, and maybe in some cases you can actually find it on websites like OpenCourse, where we actually have this kind of thing available. But everything gets a little bit more complicated because we have to start from a much lower level than we are used to when we are programming CPUs themselves. So the chips itself has a lot of connectors usually. And because we don't really have anything else to do, so we don't have necessarily to access any memory on the outside. We don't have to necessarily, we don't have graphics card, we have PCI buses or something like this. This thing can work by itself. The only uses of the fixed uses of the connections to the outside world a FPGA has are usually something like power supply. Or maybe even some control mechanism so you can program the whole thing. That's a couple of bits. The rest of the pins of an FPGA are usually I/O pins. And we can use them for whatever we want. So there might be differences in the way, in the speed and the connectivity of the pins between us. So some might be better used for something than the other thing. But in general, we can use attach whatever we want. We can have analog to digital converters, so digital to analog converters on those. We can use them to have outputs with PWM, so pulse width modulation outputs, which are used for stepper motors, so these kind of things. We can connect displays there. We can just have a single button connect to any of those. So we are completely free to design these kind of things around the problem which we are using. And so this makes it very interesting for embedded world, where the program is just stored there, and then we have a fixed set of functionality which we want to solve. We have certain types of devices which we want to control. And, well, once we solve the problem, we can just attach it there. And these chips, especially on the embedded world, they're relatively cheap. And much more importantly than that, if you think something like an ARM chip and so on, they're running inexpensively in terms of electricity. An FPGA can be even less power hungry than any of the embedded chips can be. So when because even in the most simple general purpose CPU, there's lots of circuitry which at any point in time is not really used. So they might power gate them in some way or form, but with an FPGA, we only program it to do exactly what we need. And everything else is simply unused. So we can actually use all the energy which at any point in time has to be provided for exactly the purpose and nothing else. So we have the potential of being very, very efficient when it comes to actually utilizing them in embedded workloads and in my field of work. So we're talking about machine learning. FPGAs are very useful for inference workloads. So it's not the learning part, but applying the model to something, which is not as compute intensive, but it has to work all of the world. So nowadays we have, well, let's say, we have power plugs which learn over time the behavior which you should do. Well, guess what? You can easily put an FPGA in there which is pre-trained with a model, and over time it will simply adjust to the surroundings. So that's very easily doable. So there's one piece of information which is not contained in here, And that is, well, how are all these different blocks actually connected? So if we would not have any configurability in those things, we would lose out and we would be restricted quite significantly what we can solve with that. But the good news is that the connections between these different modules, these logic blocks, so as I mentioned, there's a certain number of inputs and a certain number of outputs which have all of them, and we can route them in a certain way. And that's a major part of the reverse engineering which took place to actually be able to program this thing. The IS-40 is using this kind of connectivity between the different nodes. I'm not going into all the details. This is here just to impress you to how it actually looks like. So there are different connections, and people thought very hard how to actually. So it's not just a grid, not a Manhattan grid of connections there. There's a little bit more sophisticated, and the software which is programming this, which is creating basically the configuration for all the logic blocks and the interconnects, has to figure out how to take best advantage of this kind of communication structure between the PLVs to implement the program itself. So there's a lot of knowledge which is necessary to do that kind of thing, but this is just math basically. So there's a solver going on inside these what's called the place and route and program, which basically maps the logic which we are expressing to these implementation details, as we can see it here. So this is not really that important unless you're really interested in programming this yourself. But we have now knowledge about how this kind of thing works internally, publicly available. But what I want to go into is a little bit, at least at the high level, is what does it take to actually now program this kind of FPGA? So I mentioned at the beginning that we have the individual logic cell, which has a 4-input LUT, and therefore it needs 16 bits of programming itself. So this is what we have to provide for them. So in addition, we have these additional blocks in there which can be programmed in every single logic cell. So we have the carry enable. So this is basically the vertical line, whether we are using it at all. So there is the flip-flop. So this block which I mentioned, which I promised to talk more about in a bit, which can be enabled and disabled. We have a reset flag, so where we can reset it at all and so on, and there's an asynchronous reset flag and so on. So these are basically chip selections inside this, inside the logic block, which can be set. So 20 bits we need to program each of the logic cells. So next level up, we have 8 of these logic cells, and in addition, we have to implement parts of the connection network, which is called the local track. So again, I'm not going to details how this is split up, but in what we found, what Clifford found out over time is simply that we need for that another, 8 times 4, 40 bits for the description of the network itself. So this is the entire description of a logic block consists of these bits. And if we are providing these bits as part of the programming of the FPGA, we can control every single aspect of an individual logic block. So, and if we then look at this at the whole chip, what we need is a couple of these logic blocks, which also then govern whether we're connecting to the DRAM chip itself. We have to configure the outputs, so the connections to the outside pins, how we want to use them, which of the individual lines gets connected there, and we have to do the RAM configuration itself. This all together makes up the complete description of how the FPGA's programming works. So, but you should realize at this point, this is a different type of programming. This is not programming in the sense that, we have a program which can change and so on, these kind of things. That's actually fixing how the individual hardware components work internally. And that's quite nice. So if you're looking at this at the two-chain level, it looks something like this. We are talking about the Bitstream, which is the configuration which gets generated How this is constructed. So I already mentioned that we are programming these kind of things using what's called hardware description languages, which nowadays are coming in two forms. There's a VHDL language, and the other one is called Verilog, and together with variants like System Verilog, etc., so which exist out there, but there are basically two of them. So VHDL is ADA-based, comes from the US government and the armed services requirement there for them to have this all specified in this. And Verilog is another one which comes out of industries. It's more C-like, and so it's somewhat less verbose when you write it, but the VHDL compiler catches more static errors in this case. So depending on what you do, I actually use both of them, depending on what the problem set is. So, and you need a tool chain which can handle these kind of programs, and the output is this so-called bitstream. So, and the bitstream itself is a file which can, just like any other one, is loaded or is stored on a disk, can be there. So the question is now, how do we actually program the FPGA? In this case, the latest one, the ICE40, which I have there. This all has to be stored in the SRAM cells. So when an SRAM just means that as soon as power is off, well, the content is lost. So we have to be reprogrammed every single time. And normally, the way this is implemented for most of the cases, so for the simple ones, they are connected using USB. So there's some form of USB chip on the PCB for the FPGA module, and you can program from the outside using some form of driver. You can upload the bitstream. It gets stored in the appropriate locations of the SRAM cells, and then the whole thing gets restored, and it is running the program itself. But pretty much every single FPGA also has some on-chip flash memory, which you can store the program on, and then every single time the chip resets, it loads from the flash memory and starts running from that. So this is something which you do, of course, once you deploy the chip on the device, and not during the development phase. During development, you really want to have it always rewritten. The Linux kernel specifically over the last couple of years has gotten driver support to program even the big FPGAs. So nowadays you can even from user level program Xilinx and Altera FPGA through the drivers in the kernel with no hassle whatsoever. So that's easily doable. All right, so there's one aspect of programming which I would be amiss to not mention, and that is the concept of a synchronous circuit versus an asynchronous circuit. So in the description of the logic blocks, I mentioned this flip-flop thing there. So where does it come in? Anyway, so here in this case, I have presented to you on a gate. So in this case, it's an AND gate, and so on, with a tiny little addition where you have a delay, a potential delay. So the A signal can potentially arrive a little bit later. So now let's take a look how the signals behave over time. If we get a changing signals A and B, and how the result Z looks like. So you see on the top one, this is the input signals A and B are coming with no delay. And you see a certain input pattern A and B where the signals are always opposite of each other. And therefore, AND of them always produces zero output. That should be of no surprise to anyone. This is how, when we're thinking logic, how we imagine things are working. But in practice, because of all the capacitance and these kind of things, no single input has no delays. There are always delays. And there are different delays depending on what kind of path the information is taking. And therefore, the input signals are arriving slightly differently. And all of a sudden, and this is the second set of graphs which you see here, the output signal is not as clean as we imagine it anymore. And this is as I said, this is the case in pretty much all circuits there. We cannot control the delay of all the inputs to the precision so that we can achieve the same result as if we would have no delay whatsoever. And you can see here the output Z is differing quite significantly from what we expect this to be, just because of this delay. So I don't say it's impossible to write code like that, or in this case, so FPGA code or design in general, circuits around this, what is called asynchronous circuits, but it's very much harder, and specifically with FPGAs where you have less control over exactly the pathway on which the signals are traveling and so on, that makes it pretty much impossible unless you're spending an ordinarily large amount of time on that. So this is where these flip-flops come in. In this case, a D flip-flop, which you see here also on the bottom. So here in this case now, so I added another graph here with 4 lines. We have an additional signal, which is this phi. Phi in this case is usually some form of clock. It's a usual symbol which I used for that. So this is simple a clock which raises the signal in a certain amount of time. And the inputs, as you can see here, A and B, are just as in the case of the second one, are slightly different. So delta T is larger than 0. But because we are piping the output, instead of using it directly from the AND gate, we are piping it first through the flip-flop. The flip-flop, in this case, it's this signal, this triangle here, the connection where the phi signal is connected, means that it acts on a rising clock. So whenever the signal is rising, in this case it takes it. The output, which is the output Q here of the D flip-flop, is only reflecting the input D at the time when the clock signal is actually rising. When it is not rising, it uses the previous state. So it can be basically clocked in the new input. And that's what you see here happening on the bottom 4 lines there, where A and B, they can have a discrepancy in the way arriving, but because we are having this clock signal phi, which means that the output Z is not immediately reflected by the end of the inputs A and B, but only at the time when the clock signal is rising, we get a nice clean output as we expected. So by using these kind of synchronous circuits, which are synchronized using a clock, usually there's one clock, sometimes many clocks inside a single FPGA network. So using that, we can create with much less complexity circuits which work in a reliable fashion. So if you ever wondered why their CPUs have clocks, why they are driven by clocks, there's no inherent reason why we could not have CPUs which don't need a clock. But because of these problems, we need clocks. And that's exactly the same thing for FPGAs as it is for CPUs. So once we have this, we can build enormously complex programs inside an FPGA. But what makes FPGAs different from CPUs is really that we can have action inside the FPGA all across the circuitry. So if you think back of how when I mentioned how the 8080 works, the 8085 worked, so you saw these highlighted blocks going on all the time there. So, but at any point in time, only a few of these individual blocks have been highlighted and were active. So with an FPGA, in theory, yes, if we wanted to, we can implement the same thing. But if we have a well-designed program which matches the FPGA, we can have all of these kind of things happening at the same time. So this opens up a completely different type of programming. So the example which I like to always mention in this case is, for instance, if you have some form of network monitoring problem. So you are specifying a regular expression which you want to match against the incoming traffic of a network. So how does it work on a CPU? Well, you get the input, you execute the regular expression on the input, then you go to the next input one. So, well, this sounds good, but the regular expression can be complicated. For instance, it can be something like if it's this word or this word or this word and this word, there can be 1,000 different words, and each of them has to be compared against the input sequentially, because this is how a CPU works. On an FPGA, we can do it differently. We just pipe the input, which comes from the network, into 1,000 different little matching engines which are working on the FPGA, which can be implemented there, and they all at the same time are operating the same kind of operation. They can match it against their respective word. So this is a different type of thinking when it comes to actually programming. So the FPGAs are much, much more powerful. So here's an example of how this can work, and this is the kind of program which I would show normally on the board itself. So this is written in Verilog. It's as I said, and it's not about the programming and so on, but the main thing is that this is a very different way of thinking from what normal software developers are used to. We are doing things based on events, etc. So not in a sequential way. So these blocks which you see here, they can happen at the same time, and that's the best way of programming this. To take advantage of this, we can use the tool chains which we have available. So these are the individual steps. So the first one is called is the synthesis, which gets into a common format. Then comes the place and route case. In this case, we have then optionally a timing analysis, which makes sure that we can actually run the clock of the FPGA at the highest possible level. Then we're creating the bitstream, and then we can program the whole thing. So along with the tool chain, we have visualization tools where we can actually see how the program gets programmed on the FPGA, which of the individual blocks are there. So you cannot really see this here, but this is it's a web page which you can zoom in and which shows you exactly how the program actually gets stored on the FPGA, how they are individually connected, etc. So you can learn all about this kind of thing. So here's a little detail from how this one little program looks at. So you can see here on the second to from the right column, this is implementing one big adder. There. So we have a couple of these logic blocks which are connected to each other. And yeah, so there are various kind of problems with actually running this. So we have limited operations available. Everything else has to be constructed. In some cases, we have hardware available, like multipliers, but not all of the time. It's very dependent on the individual chip. But that's the problem of the place and route tool. They have to be adjusted for every single chip we are going to use out there. And we don't really have an OS support in there. So we don't really have something like, bring up network connection. We have to bring all of these kind of blocks with us. So we are working on something like this. So I'm working with, I'm looking after a PhD student at Boston University right now who is working on these kind of things to make these kind of services perhaps available in some way or form, in the form of an operating system, but nothing like this exists today. And the most interesting thing for at least for me, for actually programming these kind of things, is that we can implement what is called soft cores. So we can implement our own processors on the FPGA itself. So this might be useful for processor research in the first place, but also because an FPGA, the toolchain flow and so on, this can take for large programs sometimes a day or 2 or 3 to actually complete. So this is a tremendously complex program. If we want to have fast turnaround times, we can just implement once a soft core in the FPGA, which has access to all the nice logic there. For instance, implement a regular expression matcher on this kind of thing. And if we want to change the program running on the software, that's just normal program compiling. So, for instance, what I'm using is the RISC-V soft core on my FPGAs. And I just have the C toolchain generate a new RISC-V program, which it can easily do. And I only have to upload this different program, which actually doesn't live in the normal FPGA cells. It lives in the DRAM attached to the FPGA. And that's easy to reprogram. It's a fraction of a second. So I can actually experiment a lot with different kinds of logic which I actually want to do on this kind of hardware. All right. Lots of stuff I talked about. So are there any questions? There's one over there. So do you want to go with the microphone?
So thank you for the talk. I would like to ask, what are your thoughts on the new RISC-V architecture? Is it going places, or maybe something of a slow?
No. So RISC-V is the future, undoubtedly. So we have complete access to the architecture, every single detail. We can even influence it if we want, if we have the time for that. So if you even try to implement an ARM softcore, ARM will come after you and sue you into oblivion to actually try to do these kind of things. Not the same with RISC-V. So there are other ones, OpenCore itself. But if you look at the nicety of the design of the RISC-V architecture, you see it's so much better than anything which came before. It's nicely orthogonal. It has all these nice extensions you can put into the core, just enough of the features which you want, but at the same time, it's scalable. And for me, one of the most important one, it actually has Cray-style vectorization, which no one else has. And if you do HPC like I do, that's tremendously exciting.